Hey guys, welcome to another quantitative reasoning video. This is from chapter 7. We're doing unit 7A, which is the fundamentals of probability, the basics of probability. And probability is a very simple concept. We need a couple of definitions before we get there. So the outcomes for an experiment or an observation is kind of the basic results. What are the possibilities? When you flip a coin, you could get a head or a tail. And so for example, if you flip two coins in a row, then you could get a head, then a tail, or you could get a tail, then a head. That's a couple of different outcomes, right? There's a couple other ones, both tails, both heads, whatever. And an event is one or more outcomes that you're interested in. So if you're interested in finding when you get all tails, then that's an event. The two coins tossed is one event. The two tails in a row is one event, for example. Okay. Probability is a ratio, and so because probability is a ratio, it lands between 0 and 1. The probability can never be negative, and the probability would never be more than 1, even in a more complex scenario. So when you talk about having a probability of 0, that means that it's impossible. You cannot have it happen. A probability of 1 means it's certain. In other words, it's definitely going to happen. And then, of course, in between, if you have a 0.5 probability, a 50% chance, that's half and half. Equally a good chance that it will happen versus it won't. Anything more than 0.5 to 1 is likely. Anything less than 0.5 to 0 is unlikely. But we're not going to use this terminology a whole lot. It's just getting an idea of the basics of probability. So what is probability? Probability is simply a ratio of the number of ways that A can occur, where A is the event you're looking for, okay, the event of interest, divided by the total number of possible outcomes, right? So it's the number of ways that you can get what you are interested in divided by the number of different possible outcomes totally. Okay, now this is if they're equally likely. If they're not equally likely, then we have to do some maneuvering to get there. So the idea of probability is very, very simple. To be honest, the most difficult part of probability is counting, which sounds silly. Please don't go home and tell your parents that you learned how to count in math class today at college. But that's really where the challenge comes in, believe it or not, and I'll show you why here in just a little bit. So a couple of simple examples. Finding the probability of an outcome for an experiment. Your experiment is tossing two coins. You flip two coins. So there's 4 possibilities. You get 2 tails, which is no heads. You get 1 head second. You get 1 head first, or you get both heads. Those are the 4 different possibilities when you flip 2 coins. What's the probability that you're going to get exactly 1 head when you do that? Well, the probability, how many different times do you get exactly 1 head? Here's 1, and here's 1. So that's 2 ways to get what you're looking for out of how many different things? There's 1, 2, 3, 4 different possibilities that you could come out with. So it's 2 out of 4, and we would usually reduce that to 1/2. Simple enough. Okay. How about getting a 3 when you roll a single 6-sided die? There's 6 different sides. Each one has a different number. One of them is a 3, so there's only one way to get a 3 out of a total of 6 sides. And so the probability that you get a 3 is 1 out of 6, or 1/6. Unless it's otherwise specified, or unless the problem itself gives you probabilities that are in decimal format, please keep them in a fraction format. It helps me to be consistent in the grading. It also helps you in being consistent and understanding what it means. Okay, so please express your probability values as answers. Please write them as fractions unless the problem itself gives you probabilities using decimals or a percentage in the problem. Okay, and you'll see some of those here later on. So playing cards are a very, very good way of determining probability and practicing probability. However, I know not everybody has the same experience with playing cards. So if you do not have a good familiarity with playing cards, get online, Google a set of playing cards, pictures, image of deck of playing cards, and go ahead and print that out for yourself. Take a screenshot of it, whatever. but put it in your notes so that you've got it, because you've got to know the basics of cards in order to do the probabilities. So a standard deck of cards has 52 playing cards. There's no jokers. All right. There are 4 suits: heart, spade, diamond, and club. Clubs and spades are black cards. That's the color of the stuff. Hearts and diamonds are red cards. That's the color of the numbers and stuff. And again, these are traditional playing cards. I'm not talking about if you have like a Harry Potter deck or something goofy like that, then they're going to look a little different, but you need to know the basics here. Every one of the suits has cards for all the numbers 2 through 10. Plus there's a jack, a queen, a king, and an ace. There's a total of 13 cards in each suit. So you can think of the ace as high or low. That's not important for us. We're just counting the total number of cards. Okay. As I mentioned, diamonds and hearts are red. Spades and clubs are black. And so, and one other piece of lingo, jack, queen, king, usually those have pictures of them. Those are sometimes called face cards. So if you're ever asked for a face card, that means it could be a jack or a queen or a king. Not an ace, but one of those 3. That's a face card. That's terminology with cards. And that's about all that you'll need to know. Okay, so the question says if you draw one card at random from a standard deck, what's the probability that's going to be a spade? Probability that's a spade. Spade is our experiment. Our spade is our outcome. The experiment is drawing one card. So how many different spades are there? We just talked about this. There are 13 cards of each suit, so there are 13 spades. So the number of ways you could get a spade, 2, 3, 4, all the way to 10, jack, queen, king, ace. There are 13 ways to get it. How many different cards are there? 52 cards. So the probability that you get a spade is 13 out of 52. If you draw a random card, that reduces, 13 goes into 52 4 times. And of course that makes sense. There's 4 suits. They have equal number of cards in each suit, so it should be 1 out of 4. That makes sense. But 13 out of 52 technically is the way that we would start with it and then reduce it down to 1/4. I do expect you to reduce your fractions. Okay. So I talked that counting is the challenge, and so one good way of helping you determine the number of items possible is to make a sample space. A sample space represents all of the possible outcomes to an experiment, and we use these when the outcomes are either difficult to kind of enumerate or when the outcomes are not equally likely. And that's the example that I have for you here. Here's a sample space. Assuming there's an equal chance of having either a boy or a girl at birth, what is the probability of having 2 girls and 2 boys in a family of 4 children? So first of all, let me please state that we're talking about, I don't want to get into the gender challenge here. We're talking about biologically, we have determined that there are 2 different possible outcomes at birth, a girl or a boy. I'm not talking about or even attempting to discuss gender identification and the continuum of gender and non-binary type of things like that. That's not what we're talking about. We're trying to just do a math problem here. And so we need the 2 different things here, boy and girl. So assuming that you have 4 kids and the probability of having a girl or a boy biologically at birth is 50-50. And so it's not exactly 50-50, by the way, but it's easier. We have to have that for our probability to work well. Okay, so we have 4 kids. Then what we do is we list out all the different possibilities. You could have 4 girls in a row. There's only one way to do that, have all 4 girls. But to have 3 girls and a boy, there's actually 4 different ways, because the boy could be last or third or second or first. So there's 4 different ways that you could have a boy with 3 girls in the family. 2 girls and 2 boys, there's actually 6 different ways. And so you kind of have to go through the process, kind of like we did with our truth table, the true, and the true false, that kind of thing. We have girl, girl, boy, boy, girl, boy, girl, boy, girl, boy, boy, girl. So you just have to list these out, and we'll come up with a little bit better way of writing it out methodically. We'll talk about that in the next chapter. But anyway, there are 6 of those. There's 1 girl and 3 boys. There's 4 of those. And then to have all 4 boys, there's only 1 way as well. So there's 1 way to have all 4 girls. There's 4 ways to have 3 girls and a boy. There's 6 ways to have 2 girls and 2 boys. There's 4 ways to have 1 girl and 3 boys, and there's only 1 way to have all 4 boys in a family of 4 children. So then what is the probability that you have 2 girls and 2 boys? You have an equal number here. What's the probability of that? That's your outcome that you're looking for from this experiment of having 4 kids. Well, how many different ways are there to have 2 girls and 2 boys? There's 6 different ways to have 2 girls and 2 boys. How many different total possible outcomes are there? 1 plus 4 plus 6 plus 4 plus 1. Add them all up. If we add these all up, we get a total of 16. All right, and that makes sense because there are 2 ways to get the first, 2 ways to get the second child, 2 ways to get the third, and 2 ways to get the fourth. That's called the multiplication principle. If you want to know how many different possible combinations for boy-girl there are in a family of 4, there are 2 choices for the first kid, 2 choices for the second, etc. This is 2 to the 4th power. That's 16. Okay, so that makes sense that it's added up to 16, but they're not all equally likely. That's why we had to make a list. And so we get 6 out of 16, which of course reduces to 3 out of 8. And the probability of having 2 boys and 2 girls in a family with 4 children is 3 out of 8. Okay, so that's the process, and so that's how laying it out is important. Now, the second example here gives us the opportunity to look at rolling 2 dice at one time. And when you roll 2 dice, what we typically do is we add the 2 numbers together. So if you roll a 1 and a 3, you get a total of 4. But if you roll a 3 and a 1, you also get a total of 4. Or if you roll a 2 and a 2, you get a total of 4. So there's more than one way to get a 4. There's more than one way to get a lot of these numbers. And so what we need to do is we need to make this chart. So we basically have, this is like our first die. And sometimes you can't tell the dice apart, but for our purposes, we need to think of being able to tell the dice apart. And so we have our first die and our second die. We roll a 1 and a 1. What do we get? We get a 2. We roll a 2 and a 1. We get a 3 total. We roll a 3 and a 1. We get a 4 total. And so you can go through this entire process and list all of the different possible outcomes. Now, I'm going to save us a little bit of time and not do that. Okay, we're going to get rid of these. And we'll see all of the different possible outcomes here. So when you roll a 1 and a 1, you get a 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, etc. Okay, and notice they've highlighted the 8s because, for example, if we wanted to ask the question, what's the probability of getting an 8? Probability of rolling an 8 is equal to, well, how many ways are there to get an 8? 1, 2, 3, 4, 5 ways. Yeah. How many different possible outcomes are there? There's lots of the same numbers. There's 5 different ways to get an 8, but there are 36 possible combinations of numbers that we could possibly get. And so 5 out of 36 is the probability that you get an 8. All right, so here's what I'd like you to do. Here is 3 different probabilities that I'd like you to calculate based on this sample space from the previous page. So what I want you to do is I want you to pause the video, okay, maybe take a screenshot of this or pause the video here and write these down. Go back and forth however you want to do it, but I want you to find the probability of rolling a 7, the probability that the sum is odd, or the probability that you get a 5 or a 10 for the sum. These are all sums, not rolling a 7 on one dice. That's impossible, right? But they're rolling a sum of 7. Okay, so here are your 3 probabilities. Questions, hit pause. All right, and then if you need to go back in the video, then you can look at that sample space, okay, or take a screenshot, take a picture of that real quick, and then come and answer these 3 questions. Hit pause, and then we'll go over them together. Okay, so rolling a 7. What's the sum of 7? I count how many 7s there are. 1, 2, 3, 4, 5, 6. There's 6 7s. And so I get 6 out of 36. They're all out of 36. And that reduces to 1 out of 6. Okay. Find the probability the sum that you roll is odd. Well, odd numbers would be a 3 or a 5 or a 7. 7, 5, 3. 5, 7, 9. 9, 7, 5. 7, 9, 11, 11, 9, 7, okay. Every other number's odd. Well, if every other number's odd, then there are 18 of those out of 36, and that's a probability of 1/2. Finally, finding rolling a 5 or a 10, or we'll deal with compound probabilities later in the next section, but really, we just need to go and look, okay? Where are the 5s? Here's a 5, here's a 5. Notice they're all on diagonals. There's a 5, 4 5s, all right? How about the 10s? Here's a 10, here's a 10, here's a 10. So there are 4 5s and 3 10s, and remember that it's or means one or the other or both. You can't get both this time, but you certainly can get 7 total, 4 5s and 3 10s. That's a total of 7 out of 36. That does not reduce, and so that's the probability. Okay. The last thing I want to talk to you about from section A is the probability of an event not occurring. Remember that something has to happen. When you roll a die, something has to happen. When you flip a coin, something has to happen. So the probability that you get something is 1, which means that if P of A is the probability that you get A, the probability that you do not get A is the rest of the probabilities, everything else, right? And so they have to add up to 1. And so if you take the P of A to the other side, basically, you get 1 minus P of A. So another way to write this is the probability that A happens plus the probability that P of A does not happen has to be 1. Right? Either A happens or it doesn't. Something else does. And so those two have to add up to be 1 because 1 means something happened. 1 is the highest probability you can get, right? So in the book, they calculate for a family of 3 children, the probability that you have 1 girl and 2 boys is 0.375. So what is the probability that you do not have 1 girl and 2 boys? Well, if you had to count that up, guys, that would take a while, right? Because you would have to say, wait a minute, the probability of having all 3 girls, the probability of having all 3 boys, the probability of having 2 girls and 1 boy, all the differences, right? And you don't want to have to do that. So what you're going to do is you're going to say, okay, that's 1 minus the probability that we did have 1 girl and 2 boys. And that probability was already calculated. So we get 1 minus 0.375, and that's 0.625. All right, again, when the probability is given as a decimal, I'm fine with you reporting it as a decimal, but otherwise you should report it as a fraction, okay? So get into my math lab, play around with 7A. You've also got worksheets on 7A and B together, and we're going to go through 7B next. So you might want to play around with 7A in my math lab a little bit, but then watch the video on 7B, and you'll be ready for both A and B. All right? Thanks. See ya.